A couple of corrections. You are allowed to correct me as I have asked you about during my talk. Let me see. Someone thought, I think that's related to my writing, that this could look like a cow toss model, which of course would be much more funny and challenging. but actually, it's of course coin tossing. I'll try to concentrate on my writing. Also, another little thing, more severe for the confusion level, was since I was counting the number of heads to be 6 in this expression here, I should not see how many times I could take 0 out of 6. I could see how many times I could take 6 out of 6 for the formula to make good sense. Luckily, it's the same thing, so I wouldn't make any error. But for the formula and the whole thing to make good sense, using the binomial formula with x equals 6, n equals 6, and p equal 0.7, then I need to put a 6 there to be strictly correct. And also, I was not, this is B, I may be not a good writer here, B-I-N, and now it's even less. Maybe I should use capital here. That's a bit more easy for my... I missed the part in school where you were taught writing nicely. That didn't quite interest me, and I think they gave up on me on that. And so I don't know how to hold it. I don't know how to write it. So computers were fantastic to me anyway. I'll try to do my best here for you not to get hurt by this lack of ability that I have. Next point was, or is, the hypergeometric distribution. Let me just jump back to this slide that I jumped a bit fastly before, where I say binomial distribution comes up in relation to statistics when we're talking about sampling data, like I did before with the sampling whether you were left-handed or not. And then you count how many are left-handed, and you have something which is really binomial, because you sample at random. But this only holds for the binomial if you sample one at a time with replacement, such that you don't change the system. If you sample one and put them to the side and sample the remaining ones, then you change the system so the underlying P is now no longer the same. So, strictly speaking, and for real sampling here, or if you do quality control in a company, you don't sample one and put it back with the risk of sampling it again and spending, if you're at FL Smith, maybe one measurement may cost 100,000 kroner or something like that. You don't want to measure the same thing twice if you know it's the same thing. So, I mean, common sense will tell you in many practical cases, I won't put people back if I want to check something. I'll keep them to the side, or in another way, I grab a handful simultaneously, right? That's the same as taking one, taking them to the side, taking the next, taking them aside. That is sampling without replacement. So we have another friendly candidate to deal with probabilities when this is actually strictly the case, that this is what we do. And then actually sometimes the two are not very different in some cases anyway. So the hypergeometric distribution is used also for this example. So we have, this is kind of quality control kind of example thinking. If we have 15 hard disks in some batch or some shipment, and we know, I mean, this is a bit artificial, I acknowledge that, but still, just to make the point here, say that we know this is the scenario. We could also call it a what-if scenario. What if 5 of the 15 really had a bad situation, that there were 5 defects out of the 15 samples that we have received? Would we, so now you can start, what is the chance of finding out about some of this by taking quality samples out of these 15? That's the setting we are looking at here. For instance, we decide to make a random sample of 3 of those hard disks. So I take a handful of 3 out of the 15. And then, in this what-if scenario, what if 5 of them, this is actually what we are going to call small a is going to be 5. Capital N, that's the number of things that we sample from. The size of the sample is 3. We are worried about, or interested in, I should rather say, the number of hard disks with scratches. This is the one which is hypergeometrically distributed. Let's try, before I show you the formula, it's a matter of combinatorics actually to understand the hypergeometric distribution. If I'm interested in this case, what is the probability of having exactly one of the 3 being a defect, being one of those with scratches? How can I find this probability based on combinatorics? Well, I have to count, first of all, how many different possible samples of 3 can I take out of 15, right? How many 3 groups out of 15 are there if I take them at random? How many different are there? Well, we had a name for this. This was 3 out of 15. This is the sort of the typographics of the what you could call I'm lacking an English word here. The code for a number. I mean, it's not 15 divided by 3 for those of you who sees this for the first time. It's just the name saying 15 over 3 with capital large parentheses, right? And this is the binomial coefficient. This is the way of writing the binomial coefficient. The binomial coefficient counts exactly this number. How many different 3s are there out of 15? Well, it could be a number. If we have the 15 number, it could be 1, 2, 3, 1, 2, 4, 1, 2, 5, blah, 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 and then 2, 3, 5, 2, 3, 6. There are a lot of different 3 groups out of the 15. We can count them, given by this number, the binomial coefficient. Well, that's all the possible outcomes. Then we need to count how many of these outcomes would have exactly one defect in them. Well, how can it happen? Then I need to take 1 with scratches out of the 5 with scratches which are there. And the remaining 2 I have to take out of the remaining 10, 15 minus 5. The remaining 10 that have no scratches. And then you just have to start playing around with factorials here if you want to do this on your own. We could do just one step here. This would be 5 factorial. We take the 1 divided by 4 factorial divided by 1 factorial. The other one is 10 factorial divided by 8 factorial divided by 2 factorials. That was the 2 upper binomial coefficients. Now I take the one in the denominator. Then it's 15 factorial here, and then 12 factorial and 3 factorials. And then we can start playing around with fractions if you want. That's pretty nice. It's like playing some computer game or something like that. That's pretty interesting. I don't want to do that now. I have the number for you. I get the number 45 out of 91 if I did it correctly, which is then 0.4945. Almost 50% chance here to actually find one of them. That was just as an example for playing around with the hypergeometrical distribution. Here is the general description now. We have a population size of n, 15 in our example. We take a sample of size n, small n, which was 3 in our example. We had a known situation to be able to do explicit calculations. We had this thought scenario of what if there are actually 5 defectives out of the 15 so 5 out of the 15 are defectives, meaning that 10 of them are non-defective, right? Then the formula that I just gave you in its general form, not using the numbers, but using the letters, looks like this, but it's just the formula that I just illustrated for you in use. There is a notation for saying that something has the hypergeometric distribution like this. If, that's the point I wanted to raise. The reason why, actually, it's not always used a lot, the hypergeometrical. It can be used when you sample populations that are not too big, and you have a sample of pretty large sample, it can be reasonable to use, or maybe you could say you should use the hypergeometrical. However, if I sample, say, 10 out of a population of 1 million, say, I have a lot of animals out there, and I'm a veterinary epidemiologist, and I sample some animals in my herds to test whether they're sick or not. And then if I sample 10 out of 1 million, I don't actually, in practice, have to worry about whether I sample it with or without replacement. Because putting an animal back to be 1 out of 1 million doesn't change anything. Mathematically speaking, it's not the same. But when you do the computations in the binomial and the hypergeometrical, it will give you the same result anyway. Because it's just on the decimal point, maybe 15, 16, or 17, that it makes a difference. So in real life, it wouldn't make a difference. That's why it's often seen that the binomial is used a lot. Even though, strictly speaking, the hypergeometrical should be the tool to use. But often you can use the binomial without worrying, because it just gives you the same result as the hypergeometrical. So that's just, we'll get back to that when we we've been there, we've done it, we've seen it. That was the one I just did before. This ended up the hypergeometrical part. So George, we jump quickly to the next.